Hi class, so I've decided to re-record the video so that way I can actually go on here on the PDF and point out things that I had mentioned in class. Unfortunately, we didn't have the situation with the with the light bulb, and so we'll just deal with that. I'm also going to I have a plan in the event that it happens again. So basically now we're gonna, as I mentioned in the last class, we're gonna combine everything together. So we learned all about, we've learned about C code to MIPS. We've learned about the arithmetic logic unit. We've learned about how the instruction flows. We've learned about performance and how the computer runs. So we learned the 5 stages. So we break them down in this manner. We have the instruction fetch, where in this case, this is topic object of 5.1. So the program counter, it contains the memory address of the next instruction. In the beginning, the program counter sends the 32-bit value read address, and then it's incremented by 4 because of this byte addressing, right? And then the instruction memory is what contains all the instructions. So from the previous lecture, from the previous section, we had mentioned we combined C into assembly language, and we put it all in here. So that's typical guide objective 5.1. Program counter goes to read address, and then a 32-bit instruction comes out. The instruction decode stage, we're going to take this value, is going to be broken up into the opcode, RSRT, and RD, and then we're going to use 2 control signals, register destination and reg write, to indicate whether or not we're actually going to read it. So as I mentioned, ART and I-type have the first 5 bits as the RS value, but then after that, 20 to 16, we have to decide whether or not we're going to go to read reg 2 or write. So we need to have a control signal it's a 1-bit control signal and takes 2 5-bit inputs in. It's a multiplexer, so 0, it's going to have 20 to 16, like it says here, and then 15 to 11 is going to be down here. And so that control signal is known as register destination, which is TGO 5.3. TGO 5.2 we formally define as used to indicate if a register has been written to or not. If 1, then the register is being written to. If 0, no register is being written to. TGO 5.3 is register destination, commonly abbreviated as regdest, used to determine if the RT or RD register is being directed to the right register. Controls a MUX. If it's 0, it's an I-type instruction, and the instruction 2016 is sent to the right register. If it's 1, that's an R-type instruction, and instruction 1511 is sent to the right register. So then we also need this 2-bit ALU op, and that's because we have 15 to 0 being sent to the opcode there, to the ALU op for the control signal. It also, the 2-bit ALU op is generated by the controller and is then eventually set to the 4-bit from the ALU. So if you recall from section 3, we were discussing the arithmetic logic unit, where you have if it's 0, 0, 0, 0, it's a certain instruction, 0, 0, 1, 0. And remember, 0, 1, 1, 0 is the difference here between add and subtract there. So they're all the same except for 1 bit. So in this case, ALU op is a 2-bit control signal sent to an ALU control with the function from the instructions. That's the 6-bit function. And then it's used to determine the control signal input to the ALU. From here, 5.5, I'm going to zoom in so you guys can see exactly what this is. So coming from the instruction memory of 32-bit output, 25 to 21 goes here. 31 to 26 contains your control signal. 20 to 16, it always goes to read register 2. But then we split off here, 0 and 1. Instruction 1511, it's okay, INSTR 15 to 11. And in fact, on the exam, typically what students will write is comes out of instruction memory, and they'll just write 31 to 26, 25 to 21, and it goes into read register 1. So all this can be read reg 1, read register 2. This can be read data 1 and read data 2. This can be write register, write data. So 15 to 0 goes down here, and it's sign extended, the 16 to 32. And then 5 to 0 is the function that goes to the ALU control, which also has a 2-bit ALU op input. And this is from chapter 4 in the textbook. So we want to go into chapter 4. The textbook does an excellent job, much better than it does of the other sections, of describing precisely how the data path works. So you definitely want to help. This will help you out reviewing this significantly. So then 5, that's TGO 5.5. 5.6, we need a differentiation between the read data 2 output, which is that RS value, and the immediate value, which we also use for add I, which is immediate instructions, or load word and store word instructions. So this ALU source, topic objective 5.6, is used to differentiate between the read data 2 output and the sign extended instruction as the source for the second ALU input. Going down to 5.7, we have the same thing here. What we're doing is we have the registers coming out, read reg 1, read reg 2, write register, write data. This add, this is PC, and that's 4, right? So that's coming out here, and then we branch it off, branch off the bus. So this is PC plus 4. And then what happens, we have the sign extended value here. And then if it goes there, it's in the input. But then we shift left by 2, which is we're taking that value. So let's say we want to branch by 5 instructions. So 5 would be the value in there, comes in there, it's 5 times 4, and goes in there. So this is PC plus 4 plus immediate. And this goes into the ALU source. This ALU operation is the 4-bit output from the ALU control. So typically you'd want to draw it down here, and this is ALU control, and then you have a 2-bit ALU op input. And then the ALU out result and 0-bit. And to answer a question that was given in class, we will discuss later in section 5 just precisely what we're going to do with overflow. I'll leave this here for a second, so if you want to press pause to draw it. And so this is kind of what I was talking to you about with this game Civilization, so about carry bits. So it's an Atari 8-bit video game system, and what's going on here is that you have to build an empire to stand the test of time. So realistic interpretations on past events and historical figures. So the MOS Technology 6502 CPU, which you can look up and actually see how the data path works. Since memory resources were limited, designers had to use the good design requires good compromise design principle. So what they wanted to do is they wanted to improve performance and limit the amount of memory that was required. So in this case, the instruction set required 2 cycles for an unsigned operation. So if we recall, for the average CPI, we'd have the cycles per instruction is 2, and CPI for signed is 3. So to improve performance, the designers used unsigned integers as much as possible. However, as part of the game, each historical figure had an aggressiveness, and Gandhi is an example of peace of pacifism, had a score of 1. The designers used an unsigned integer of 1. So later, as part of the game, when the country became a democracy, the aggressiveness factor of that country was subtracted by 2. So as you know, we would perform 2's complement here to get 1, and we add them together to get this value. Now, if this were a signed integer, we would perform the 2's complement, and this would in fact be -1. However, they stored this result in an unsigned integer. So what ended up happening is that Gandhi had an aggressiveness of 255. And so they had a trade-off of 1.5 of improved performance. However, it didn't perform the correct operation. So these are the two things I read here. Very well, you will mobilize our armies for war. You will pay for your foolish pride. This is Gandhi saying this. In greetings from Mahatma Gandhi, ruler and king of the Indians, our words are backed with nuclear weapons. So, and this is why knowing that good design requires good compromise is important, especially in the light of the make the common case fast. So here, based on what you've learned so far in advanced visual systems, you understand the importance of the arithmetic logic unit, storing things in signed and unsigned integers, how you're going to store that in the register, so you're trying to maximize memory, and how that needs to be accounted for when you're actually performing the operation that the user needs. So if the coder doesn't understand how the architecture works, he or she subtracts the two values, and as a result, they think they're writing correct code. As it turns out, they aren't. They have made Gandhi into a genocidal maniac. And so this next stage with data memory, so you've completed the calculation in the arithmetic logic unit. So now we've got to decide whether to store it in data memory or if we're just going to store it back in the ALU. So memread and memwrite are control signals used to determine whether the information stored in data memory will be written to or read. Seems pretty straightforward. Read 1, write it's 1, and they're never going to be both 1, ever. So don't make that mistake. So branching is if a control signal is used to determine if the instruction is a branch or not. 1 if it's a branch, 0 if not. And here I'm going to zoom in on this here. So what's going to happen is you have your sign extended value goes here. You have ALU source. Here read data 2, read data 1, shift left by 2. It's added to PC plus 4, and this value goes to a multiplexer. Now the 0 bit, which is used to determine if the condition was actually met, and then we have the branch control signal. The arithmetic logic unit sends the result here to the address and goes past it, and this is the value we'd be using if we are in fact performing like an R-type instruction. Now RD2 comes through here and goes to write data. In the data memory itself, which you learned about in section 4 with you have direct and set associativity, cache memory, that's all accounted for here. So what we're actually going to be worrying about is that you send this here, it's the actual address. And then we're writing the data here, and then we're reading the data on the output. So this would be what we would be using for a load word, and we would be storing it or writing it there if it's a store word. And then memread and memwrite are the control signals. And so I'll give you a split second. You can pause if you need to draw this. This is TGO 5.10. Okay, so now we're going to do jump and memory to register. So this is 5.11. A jump control signal is used to determine if the instruction is a jump or not. 1 if it's a jump, 0 if not. Memory to register is the last one, and we're going to discuss this. So this either has the output from read data and data memory or the result from the arithmetic logic unit, and is written to the determined register. And so I'm going to zoom out here. This is the table. You can recopy it. I added, at the behest of a student, I had to jump here, which is we don't care, I don't care, I don't care, I don't care. ALU source, register destination, I don't care. Mem to register, because reg write is going to be 0, mem read is going to be 0, mem write is going to be 0. Branch is I don't care. ALU op, I don't care. I don't care, because we would have another jump control signal here where 0, 0, 0, 0, 1. As long as you're making sure you're not writing to anything, it doesn't really matter what anything else is. And so I'm going to upload this on Blackboard in a moment. This is the last TGO that we covered in class. And so I want to go over this in detail because this combines everything together. This is how it's all done. So you have the program counter here. And then what's going to happen is you have PC plus 4, and you add. PC plus 4 comes over here, and then we split up the instruction. Remember, we have the read address, and the instruction comes out. So you have 25 to 0. Now this is your jump addressing. So you shift left by 2, so that comes out as 28 bits. And then I'm going to zoom in here really quick. I know you're probably drawing this, so please bear with me. If you recall this diagram, this means concatenation, right? So that's 31 to 28, and this is 28 bits and 32 bits. (31 to 26) is the control signal, is the controller. All of these control signals here, 3, 4, 5, 6, 7, 8, 9, all come from this. So what we're going to do here, first of all, it's going to be, we can say mem read and mem write. All of those come from the controller. So what we're having here is we are now doing PC plus 4, and this comes to add. It also branches off here, so it would go through jump. So we would calculate, this is the jump address. So if jump is 1, what's going to happen is, as long as reg write is equal to 0 and mem write is equal to 0, then I don't care what you're doing here, I don't care what you're doing here, I don't care what you're doing here, I don't care what you're doing here. Because what's going to end up happening is you're going to have PC plus 4, it's going to add, this will concatenate with the value that comes from the instruction, and it goes to 1, and then it comes back around like this. Next, so doing this again, we have 31 to 26 goes to controller. 25 to 21 always goes to read register 1. 20 to 16 always goes to read register 2, or RR2. It also branches off here and goes to this control unit. We start to this multiplexer. 15 to 11 is the decider. If it's 0 for register destination, that means it's an I-type instruction. If it's 1, that means it's an R-type instruction. And these values, if I don't need it, for example, a branch or a store word, if I don't care, the reason why is because reg write is 0. So we have this is write data, and that's going to come back from the output of memory to register. We break off 15 to 0, so then 5 to 0 is the function, and that goes to ALU control. This drawing down here is a 2-bit, and that is ALU op. So the 6-bit function and the 2-bit ALU op combine in there to give you the output. So bear in mind, if it's 0, 0, right, I need to worry about load word or store word. So no matter what, I don't care what the function is, so it's just going to automatically put that in there. It's going to be an addition. 10 to 6 is that shift amount, and then that goes straight to the arithmetic logic unit. 15 to 0 comes with sign extension. You have a 32-bit on the output, and it's going to go up here. What's going to happen here is you have read data 1 and read data 2. They come out of this, so we're now in the execution stage, and we have this. So the sign extended output is going to come here to 1. ALU source is going to decide whether or not we're going to use, what value we're going to use, and those two values come there. The outputs other input I'm going to expect you to draw is this 4-bit value that comes from the ALU control. The output is the value that goes to the address, and the output that goes here, which will eventually be used by the mem to reg control signal. The 0-bit comes out here. This indicates whether or not we've actually met the branch condition. The branch indicates that the instruction is actually a branch. So if a 0-bit comes out that means the add value is 0. Well, if branch is equal to 0, then it's not a branch. It's just an ALU calculation where the number is 0. Here it comes to this multiplexer. Here, this value is added here. So what's going to come out here is the value of the branch address. If it's 1, that's the value we're going to branch to. And then we start again. And this here is add. You may also, for this one as well, you may also do a plus. For data memory, what we have here is the address. When I upload this, I'll include memread and memwrite. And so what's going to happen is we have the output from the ALU going to the actual address. The write data is coming from read data to. So if it's store word, that's where we would store it. If it's load word, we go to this address and write that value to read address. And then finally, memory to register. If it's 0, that means we need the value coming from the ALU. So we then send it back here to write data. And then if it is a load word, we use the output, so it's 1. And it goes back to read data here. And so while we're going to go into combinational logic and what's going on inside the controller in the next lecture. But what I want to do here is I want to describe to you what's actually going on in every instruction. I want to go over an R-type instruction. I want to go over I-type. I want to go over branch. I want to go over load word and store word, and then jump. So jump is the easiest. I'm going to put everything else here in green, so that way I can leave these here. So jump, I generate a value from the program counter. I increment by 4. The instruction is in instruction memory. So it goes up here, 25 to 0. 31 to 26 is the control signal. Now it's going to say reg write is equal to 0. Don't write to the registers. It's going to say mem write is also 0. Don't write to data memory. It's going to shift left by 2, so it's going to become 28 bits. We're going to concatenate the 4 most significant bits of the program counter, and this value is 1 on the output. Jump is going to be equal to 1. Branch is going to be equal to 0. It's going to come through here, and it's going to go tell the program counter what the jump instruction is. For branch, we're going to do branch next. So program counter, we increment PC plus 4, and this address goes all the way over here. Jump is going to be equal to 0, so we're going to be here. It's also going to send the value of PC plus 4 there. We send the value to control. We know that reg write is going to be 0. Mem write is going to be 0. And then what's going to happen is this value, read reg 1, going to be sent here. 20 to 16 is read reg 2, and that value is going to be sent here. ALU source is going to be 0. They're going to come out here. Now these are the two values I'm going to compare. The ALU itself actually compares the values. So if it meets it, goes to 0 here, and branch is going to be equal to 1. The AND is met. So what's going to happen is it's going to select that value on the output. 15 to 0 is sent here through here because this is the branch address. It's sign extended, and then we shift left by 2, which is multiplying by 4, and comes out there. It selects the branch address because it's met all the conditions and tells me precisely which instruction I want to go to. So next we're going to do R-type instructions. The R-type instruction takes 2 of the register values and is going to actually add them and store them in a register. So what's going to happen, we have PC, we increment PC plus 4, and we go through here. R type jump is 0, branch is going to be equal to 0. So in this case, I just want to go to the very next instruction. Here, we send 31 to 26 to controller. We know that from the MIP screen sheet that value is going to be all zeros. Register write is going to be equal to 1 because we want to update the register. ALU source 1, ALU source is going to be 0. And then mem write is going to equal 0. And so what happens is we go 25 to 21, 20 to 16, register 1, register 2, we send this value here. Since ALU source is 0, we take this value and then we add it. We're going to circumvent here and go there. Mem to reg is going to be 0, and so we're going to write the value back to read data. The one important thing, we have a function, so it's adding. So we're sending this here. We get the 2-bit ALU op, and that sends the value to the controller. Let me write it in a slightly different order so that way you guys can see precisely what I mean. So I'm going to go stage by stage as though this is going through stages because it's going to be important when we get to pipelining. We add PC plus 4. It's going to go through here, jump, and branch. We send 0 hex to the control unit, read reg 1, read reg 2, and then we're going to do write register. So register destination is going to be 1. So we'll wait on that for now. We go into the registers, we get those values, and we send the value out here. ALU source is going to be 0, so we get this value. On 15 to 0, what's going to end up happening is we get sign extended. We have 5 to 0 function goes to ALU control. And let me make this orange. So it's sign extended and comes here, and since it's the multiplexer chooses the other thing, we do not select that value. It's sent here, it's added, we go here, but since branch is 0, we do not select that value. So we send this value over here. Memory to reg is 0. Now what we're going to do is we're going to select register destination. So 15 to 11 is where we're going to be writing the register to, and the value that we're going to write to that register is sent here. For immediate, let's say it's add I. I probably should be even more clear. We're going to do add I. S2, S1, S0. So what's going to happen is program counter gets the value, sends it to the controller. Oh, so that's add. We're going to do R type. So read register 1 is S1. Read register 2 is S0. It produces the 32-bit values on this output here. ALU source is 0. Register write is going to be 1. And this value is put on the output here. And circumvents the data memory, goes to 0, and comes through here. S2 correlates to 15 to 11, so that's where I'm going to write the register to, and the data is going to be the actual answer of S1 plus S0. For immediate, it's add I, S3, S2, and 10. What's actually going to happen is we get the program counter, sends the 4, PC plus 4, jump is 0, branch is 0, and it's going to essentially tell me to complete the instruction and go to the next one. So what's going to happen here, we send the add I control value. 25 to 21 is S2. 20 to 16 is S3. So it's going to be sent to read register 2 and put this in pink. What's actually going to happen here is we're going to get the value and it's going to be sent here. But the problem is ALU source is going to be 1, so it's not going to be selected. What is going to be selected is this 15 to 0. We sign extend it, 32, ALU source is 1, so it goes here. So now we're going to add the value register S2 and 10. This result goes here. Memory to register is 0. So it comes here and writes to the data, and the write register is S3. And then we go to the next instruction. load word. So here we have load word S4 8 S0. So here's what's actually going on here. Program counter, increment 4, go through here. It's not going to be a jump. It's not going to be a branch, so we're eventually going to go to the next instruction. Instruction memory, we get the opcode for load word. 25 to 21 is S0. That comes out here and is put there. S0 is the base address of the pointer. 8 is this 15 to 0, which is sign extended, and put here. And that's the value. Now, in purple, S4 both goes to read register 2 and is blocked off there. And we're going to do a write register because it's a load word. So read data 2 would come out here, but since the ALU source is 1, that value is not selected. So what happens is we add these values and we go to the address. Memory read is going to be equal to 1. Memory write is equal to 0. So that, since we're reading it, the read data value is going to be in the memory where S0 is the base pointer to the array and 8 is the second element in the array. That value is put in here. Memory to reg is 1. And then we're going to come around here and we're going to write to the register indicated by this. So that's load word. Now let's do, to conclude, let's do the same thing, but let's do store word. S5, 0, S1. So same thing, we're going to increment PC plus 4, jump is 0, and branch is 0, so we're eventually going to conclude the instruction. Send the opcode for the controller here. Read register 1 is S1. And so what's going to happen is we don't care about write register because we're not writing to anything. We're storing. So this is all, so it goes, this value goes here to the controller. So it's going to go here is, it's not going to read because, actually this is, here we go. It's going to read here and we'll tell you what this way goes. So this value is S5 and S5 is going to go the write data. That's the value of the register that we're going to store in data memory. What won't happen is that it goes here, ALU source is going to be 1. So that value does not work anymore. 15 to 0 is going to be this 0 value. We sign extend it, comes here, ALU source is 1, so that passes. These two values here are added in the arithmetic logic unit, and we get the address. Write data, so mem write is equal to 1, mem read is equal to 0. Mem to reg is don't care because reg write is going to be equal to 0. And then last and certainly not least, do that. All right, I'm going to upload this and make sure that that video, this picture is there, but you should be able to have this pretty clearly there. And I will have mem read and mem write put in on this drawing.